Hello, everyone, and welcome again for our Space Brain Hack event. Today, my name is Ayub Hamoudi. I'm the bilingual program manager at EcoSchools, and I'm very happy and pleased to be your facilitator for today. For those of you who don't know about EcoSchools Canada, so EcoSchools Canada fosters students' leadership, reduces schools' environmental impact, and creates sustainable communities. Our award-winning program, aligned with the Sustainable Development Goals, reaches nearly 1 million students yearly. And we support engagement across all levels of education sector through workshops, webinars, resources, and campaigns. And if you haven't yet joined our growing network, we invite you to start your adventure on our user-friendly platform, exploring multiple resources and taking action. I would like now to hand over to Isabel Julian as advisor to tell us a bit more about the brain space hack. Donc, j'aimerais maintenant donner la parole à Isabelle Julian, conseillère en communication scientifique, pour nous en dire un petit peu plus sur le Creuse-méninges Spatial. Donc, Isabelle, à vous la parole. The floor is yours.
Merci, thank you. So, bonjour, hello everyone. My name is Isabel. I am a science communicator at Environment Canada. And I'd like to kind of challenge all of you out there. Alors, ceci est un défi pour tout le monde. So the challenge is this, is we love to explore space. Space is cool, okay? L'espace, c'est cool. On veut l'explorer. But the way we explore space can have huge environmental impacts, right? So launching satellites, sending up rockets, sending up astronauts, les impacts environnementaux sont énormes. So the challenge is this, is, well, how do we make it greener? How do we make it better for the planet? And some people are going to say, well, just don't send anything up in space. It's not a good solution. And my friend Chris is going to explain why it's not a good solution. A lot of the information that we need to protect the planet actually does come from the satellites and other missions that Ara, our friend from the Canadian Space Agency, will talk about as well. So we can't get rid of satellites. So how do we make them better? And that's what the space brain hack is we need your imagination. On a besoin de votre imagination. So if you go to the website, we have a whole program on how can you help us figure out how to green a satellite mission. So a satellite mission has 5 phases. Il y a 5 phases dans une mission satellite. We have the design phase. C'est l'étape de la conception. We have the build phase, l'étape de la construction. We have the launch phase, l'étape du lancement du satellite. We have the operation phase, le temps de l'opération du satellite. We have the decommissioning phase, where we take it apart and get rid of it. On a le mise en hors service. So each of those phases has environmental impacts, and we need you to pick one and tell us how we can make it better. So if you think you're up for the challenge, kind of poke your teachers and say, teacher, help us out. We want to do this. And your teacher can find all sorts of information on the website as to how to go about it. You have until Friday, February 28th, 2025. Alors, vous avez jusqu'au 28 février 2025 to kind of give us and send us as many ideas as you possibly can. Because sometimes us old scientists, we're in a little box and we don't see things very well anymore. So we need some bright minds to kind of open up the floor and let us see things that we might not have seen. So if you have any questions, si vous avez d'autres questions, the website was dropped in the chat. So le site web a été mis dans le chat, and we'll be happy to answer any questions as well later on after the panel. Merci, thank you.
So it is with profound gratitude that we will now introduce our panelists from today's event, Aradhana Shuduri and Chris Dirksen. Let's start with Aratana. Ara is a senior system engineer for the Wildfire Sat Constellation mission and the Canadian Space Agency. With a PhD in laser physics, she is a space tech with a specialization in using lasers and infrared sensors to track wildfires from space. Ara's job is all about creating cool tech to spot and study wildfires, making sure that satellite data is super accurate, and working with a team of experts to push the limits of space science. Ara loves solving tricky problems and is pumped to be part of this groundbreaking mission. Ara, the floor is yours.
Hi, everyone. It's a pleasure to meet everybody. Today, we're going to talk about greening space missions from phase A to F and beyond. Slide 2. There we go. So I want to, first of all, introduce you guys to one of my favorite satellites ever. This is SciSat. And this is the solar panels of SciSat on the right side. So you see what the size of the satellite. And it was originally supposed to work just for a handful of years, maybe a maximum of 5 years, but it's been going 20 years strong. And it has made a huge impact in the ozone depletion recovery. And the data is still useful to scientists all over the world today. It measures ozone and other atmospheric trace gases that contribute to the ozone depletion and climate change. And every day we find new things that come out of this data, and it's just going and going and going like the Energizer Bunny. So SciSat was launched in 2003, and there's 2 instruments on board. And there are 450 universities, institutions, research groups that work with this data. And it orbits the Earth 15 times per day at an altitude of 650 kilometers above the surface of the Earth. So it's a solar occultation spectrometer, the main instrument on this. Essentially what happens is as the Earth comes in front of the sun, you look through the layers of the atmosphere of the Earth to the sun, and you see what's changing in the sunlight, what's changing in the spectrum, what colors of gases are absorbing or emitting, different forms of light. And this solar occultation spectrometer can measure in, the parts per million, parts per billion, if it's calibrated right, all of the different gases and these trace minute gases that are there. And it's a Canadian instrument, and we are super, super proud of it. I love SciSat. But what needs to work for SciSat to work today? Like, what needs to come together? What are the puzzle pieces? So we have the science team. These are all the universities, all of the institutions, everybody that is working together to make sense of the data and also tell the satellite what kind of data we're looking for. We have the mission operators that work on 24-hour shifts. They're on the mission control system. You've probably seen a lot of movies about this. Houston, we have a problem, but instead of Houston, we have Longueuil, Quebec. And the mission operators perform all of the telling the satellite what data to take, any problems, any issues. Then we have the contractors. These are the folks that are outside contractors or companies that maybe worked on components of the mission, and we can call upon them for information or additional support when we need it. The spacecraft themselves, or the spacecraft in this case, that's orbiting, and then a huge network of ground stations, which, because you can't have line of sight, you can't even have radio waves from the satellite when it's on the other side of the Earth. But what if we want to monitor and get the data download when it's on the other side of the Earth? So this huge network of ground stations work together to collect the data, collate the data, and then send it to mission operations and science team. And also, I want to add policy and planning, because it doesn't often happen with SciSat, but it happens with other satellites where suddenly there's a natural disaster or something's going on. And so the policy and planning people at the Canadian Space Agency and at other government departments come together and say, no, we have to task the satellite to look at this specific disaster, this earthquake zone, this hurricane, and help out whoever we need to help out. And that's one example of policy and planning being involved in the mission. So, but what about before we get to space? So before we get to space, we have to worry about packaging the satellite after it's constructed, packaging the satellite, making sure that it fits with the launch vehicle, transporting it to the launch vehicle. Up here in Canada, we don't have any major launch vehicles at all. So it has to go all the way down south to Florida or to India or to the European Space Agency, all of these different places in the world where we get launches. So there's the transportation, there's the packaging, and there's the integration with the launch vehicle. By launch vehicle, I mean rocket. What happens before that? Well, for the longest time ever, a group of engineers, scientists, everybody sits together and designs the satellite, designs it, manufactures it, tests it. And so this is where we go into the mission life cycle. What Isabel mentioned about the phases is absolutely correct. And we can break them down a little bit further. And most of a satellite's mission design part of it happens way before the launch, years and years and years in advance in some cases. So we start with mission analysis. So first, I want to study ozone gas. Well, okay, but what kind of ozone gas? With what precision? How many times a day do you want to measure it? And we come up with a cool idea of something that we need to measure or we need to do. Then there's a feasibility study. The feasibility study is sort of involving engineers, scientists, and everybody and saying, hey, I want to study wormholes in space. Well, fantastic, but we don't have the technology to study wormholes in space yet. So we need to make sure that every part of the mission that we want to do is feasible and it can be done with the technology and the budget. Budget is a big part, the money and the engineering resources we need to get it done. Then the long phases, which is phase B, C, and D, and B and C, the most important, is where the mission is designed. So you start with, I want 1 satellite, 2 satellites, 3 satellites. How many of you want? How big are they going to be? What kind of instruments they're going to have? Right down to, I will have this screw in this place, and I'm going to, open the shutter and look at the sun for 3 seconds at a time, like right down to the last detail design. After that, we have to test. So I want to talk about testing here a little bit. It's very, very important because your satellite is experiencing so many extreme environments. So you start with the launch and think of the worst roller coaster possible and like make it 50 times worse. And it's, burning and freezing at the same time within like a 10-minute time period. So what we do is that a lot of times we're going to put the satellite together and we'll do something called a shake and bake. So we cycle the temperature. So we freeze the satellite down to cryogenic temperatures and raise the satellite temperature up to like a couple of 100 degrees. And then we shake it on a giant paint shaker, essentially, to make sure that nothing falls apart and it's going to survive launch. And out in space, it's going to have radiation from gamma rays and the Van Allen belts and all the other radiation going on. It's going to have extreme cold, extreme heat, thermal problems. It's going to have a lot of extreme environments associated with it. So we test all of those. We test corrosion. There is corrosion in space. We test radiation. We test all of these things. And then the satellite is qualified to fly. So then we integrate it with the launch vehicle. It's launched. And hopefully it's alive by the time we get to orbit. And then we do what is called commissioning, is we turn on all of the systems one by one, make sure everything is working. And then the commissioning team hands everything over to operations. Now, all of the mission operators, the ground stations, the science team, everybody can work together and do the lifetime of the mission. And usually that's like 3 to 5 years. And the design phase will like 10 years. But in the case of SciSat, for example, we're 20 years and going. It's amazing. And finally, we get to the end of life. What do we do with the satellite now that it's dead? Well, we better plan for it before the satellite runs out of fuel or before the parts, deteriorate in space, before it stops working. Because you can't just leave chunks of metal and all of these items up in space in a very useful orbit where it may cause problems for other things. So I'll talk about that in a couple of slides. So the most eco-unfriendly parts of space missions are rocket launches. This is high carbon emissions, toxic propellants. A single rocket emits about 200, 300 tons of CO2 at the end of the day, depending on the type of rocket and launch facility. The manufacturing processes, these are resource intensive and waste producing, and sometimes you can't get away with it. For example, if you look at the top right, these are some satellite parts. And normally what we would do for Earth manufacturing is you would manufacture them in, separate pieces here and then weld the pieces together or bolt or screw them together. But because of the precision and the stability that we need out of these and the reliability we need out of these parts in space, a lot of times what they'll do is they'll take a huge block of aluminum and literally carve out these pieces out of the aluminum. And then, 80% of that block of aluminum is waste. Then we have space debris. This is a long-term environmental hazard, and it can actually jeopardize our future in space. There's something called Kessler syndrome, where every piece of space debris essentially multiplies because the two of them collide, and there's more and more pieces going out in every direction. And now you cannot put anything in space without it colliding into something else. The ISS has to do anywhere from 2 to 10 maneuvers a month at the very least to maneuver around space debris. And finally, it's the materials. The satellites are made of many rare earth and toxic materials. So a lot of people focus on the eco-unfriendliness of satellites because of these materials, but these are hard to replace. Sometimes only the toxic material will do. We use neodymium, samarium, ytterbium, carbon-carbon composites, hydrazine, which is a common fuel. Some satellites, some optical benches for satellites, by bench I mean the part this telescope is mounted on, are made out of beryllium, which is so extremely toxic and so extremely controlled, but it's the only material that is rigid enough and light enough to fly on the satellites. So sometimes we don't have any other options. So how can we do better? Already, a lot of educational groups, space agencies are coming together to do things, to try to find ways to do things better. CubeSats are one of this. So CubeSats are generally agile. They're developed in a faster time frame. They're smaller. Because they're smaller and they have less mass, they use less materials and they use less fuel for launch. So every kilo of launch that you save, of mass for space that you save, is saving many, many tons of carbon dioxide. They also use smaller teams, less international travel, less components, modular components, so you can use the same component over and over again without generating one-time high precision instrument that goes to waste after that. We look at agile development models. So again, modular development, teams working fast, teams working with other teams all across the world using video conferencing instead of flying all everywhere to them. We use machine learning and AI for optimized manufacturing. So a human being may not be able to come up with the perfect design on how to save material because it's down to some material shavings a few microns thick. But over time, a machine learning algorithm can learn what is the most efficient way to cut away the excess aluminum, for example, and minimize waste. Reusing space vehicles. So that's a big one with the Elon Musk's rockets. Also, in-orbit refueling. So once a satellite runs out of its fuel for any altitude maneuvers or any attitude maneuvers, back in the day, like in the satellites from the 70s and 80s and sometimes the 90s also, are just left to float out there. Everything else is good. It's just that they can't maneuver anymore. Well, what if we could refuel them in space so that all of these high precision instruments could keep working for longer and longer? And rules and regulations have a huge part of this too. So up until I think the mid 2000s, there were no rules on this. But then we settled on the rule that any satellite in low Earth orbit, which is all of these Earth observation satellites, all of these satellites that you've heard of, SciSat, WildfireSat, they have to be deorbited once their life mission is over. So we got to save a little bit of fuel and make sure that we deorbit them, and then there's a lot of friction in the Earth's atmosphere, and they go down, they burn up in the atmosphere, or they drop into the ocean, so that we don't clutter up space and create more and more hazards of these dead zombie satellites floating around just waiting to collide with something else. And green procurement is a huge part of it. I mean, think of how many laptops and computers and tools and other parts that people are using for the satellite, not just the satellite itself. I mean, the amount of hydrazine that you use for a satellite is, worth one cannon. But how many computers did you buy? So ensuring that every step of the process, we buy things in a green and recycle-friendly manner. So in conclusion, the space missions are paving the way to a greener future. We've got SciSat, we've got WildfireSat, we've got SWAT, which is studying Earth's surface water, RadarSat, which is doing emergency disaster management. And the benefits of space far, far, far outweigh the costs. I have not seen any strategy of any agency, space agency or country that doesn't rely on satellite data for crops, for water, for droughts, for everything. And it's part of our strategy on how to manage climate change. So we need you guys to teach us how we can do better. A lot of times we get used to thinking in the same patterns. We get used to saying, oh, well, I can't do anything except beryllium because of course I need beryllium all the time. But by rethinking the processes, the materials, the fuels and designs throughout all of the phases from 0 to phase F, we can incrementally improve all aspects of space missions. So we also need to ensure that the benefits of space are there for all future generations so that things don't become expensive, things don't become prohibitive, we don't pollute space and Earth enough that we can't have space missions anymore. So we need your help to go outside the boundary of what we thought was possible. Thank you very much for listening to my presentation.
All right. Thank you so much, Ara, for all these informations, going through the different steps of the space mission life cycle, also seeing the challenges, the environmental challenges that we are facing and that are related to satellites, and also the alternatives and solutions we can implement in order to make these missions more eco-responsible. And I'm sure that this is going to inspire our educators and also teachers to help you guys think about a brighter and more eco-responsible future for space missions. And now I would like to invite Chris Derksen, who is a research scientist with the Climate Research Division of Environment and Climate Change Canada. So his research activities focus on the use of satellite data and climate models to understand climate change impacts on the Arctic. And Chris focuses on looking at the snow cover across the Northern Hemisphere. And he will be the main investigator on a Canadian-led satellite radar mission focused on snow in partnership with the Canadian Space Agency. So Chris's favorite part of his job is getting out on the land for field research. He has participated in more than 25 snow and sea ice measurements campaigns across the Canadian Arctic. So we invite Chris to take the floor and tell us more about his incredible work. Chris, the floor is yours.
Well, thanks, everybody. Thanks for joining today. My name is Chris. I'm coming to you from Toronto, and I'm going to talk to you a little bit about my research and the research of my colleagues I work with here on measuring snow and sea ice from space using satellite data. And Ara gave a great overview of kind of the whole life cycle of how satellite missions are developed and all the planning processes to get them into space. I'm going to come at it from the user perspective. So I'm somebody who wants to know something about snow. I want to know something about sea ice. And as I'll show you, really the only way we can understand this in a big country like Canada is to use data from satellite missions. So I work with a research team, a large group of people, and we use satellite data and we use climate models to understand the climate change impacts on snow and sea ice across Canada. And as I'll show you today, one of my favorite things to do is to get out in the field, make measurements. Been fortunate enough to do this across the Arctic and other parts of Canada because the satellite makes a measurement and it measures some sort of unit of energy. And what we need to do is take that satellite measurement and convert it into a property that scientists want to use. So that property can be things like temperature or snow depth or all sorts of different things. And so I'll talk to you a little bit about the process of how we move from the satellite measurement into the data analysis. And really what drives all of our work is climate change. That's a real major factor. It's not the only thing, but it's a major component. So I wanted to sort of start my talk off by just reminding you that the effects of widespread warming are evident now across all parts of Canada, and we understand from climate models that we'll have to deal with more warming into the future. So across Canada, the map on the top right of this slide shows you the amount of warming that we've experienced across Canada since about 1948. That's the time period when we have sufficient measurements to quantify the pattern of temperature. And what you can see is depending on which part of the country you live in, we've experienced anywhere from about 1 to 1.5, all the way up to 3 or 4 degrees of warming. And so clearly the impacts of climate change are being felt across the country, and this manifests itself in many different ways. We see more extreme heat events, especially in the summer. It's pretty simple. When you have more warmer temperatures, you have less snow, you have less sea ice, glaciers are thinning, creates changes in our oceans. I think we've all seen some pretty devastating effects of fire events across parts of Canada during the summer. So all this to say, we have a changing planet, very dynamic planet. Things are going on all the time, and we need to use satellite data to help us understand what's changing, the rate of change, why it's changing, where it's changing, all these important questions. And I guess the final point to make from a climate change point of view is that carbon dioxide, that's the greenhouse gas that's in the atmosphere leading to all of this warming. It's a long-lived greenhouse gas. That means it resides in our atmosphere for like 1,000 years. And so all the carbon that we're accumulating in the atmosphere, it's going to stay there for a while. So we need to learn how to adapt to these changes. And so I hope that's one of the key things that you take home from my talk today. So why do we use satellite data to monitor and study snow and sea ice across Canada? Well, number one, Canada is a big country, as I mentioned already, and snow cover is really interesting because it interacts with the landscape in different ways. So what that means is that the snow in Ontario, where I live, is very different from the snow in northern parts of the country. It's very different from snow in forested parts of the country. It's very different from deep snow that we see in mountain areas. So it's really a dynamic part of our landscape, and we can get perspectives on it from space that we couldn't possibly get from making measurements on the surface. These two maps are showing you kind of the same thing, but instead of focusing on snow, they're focusing on sea ice. So sea ice is that layer of ice that floats on the Arctic Ocean. And every year it goes through a big seasonal range. So it grows and expands in extent during the winter. It melts and shrinks during the summer. These are just two different maps from 2005 and 2007, so a few years old now, but they show the spatial extent of summer sea ice. And again, we could not understand this. We couldn't visualize the changes that we're seeing and how sea ice is varying from month to month and year to year. We couldn't possibly understand this without having the perspective from space. So I think these are really cool maps that kind of show very clearly the large area that sea ice fortunately still covers during the summer. I've put an animation together here. I'm going to see how this works. It's going to look really fast and kind of choppy, but I'll play it more than once so you can take a good look at it. This is an animation of radar imagery. So Canada has a rich heritage in radar remote sensing. And what's really cool about radar is it can see through clouds. So that means we can put together animations like this so we don't have to worry about clouds blocking our view. And what we're looking at here, this is Ellesmere Island, is the big island on the left of the screen. This is the northwest tip of Greenland here on the right. So you can see the land, it sits still, it's covered by ice, a lot of it, and you can see that over the land surface. And then the rest of this image actually is sea ice. And what's cool about sea ice is as it starts to melt during the spring, so we're starting in the winter with this animation and moving into the spring, the sea ice starts to move. And you can actually see ice start to flow through Nares Strait. That's the name of this strait that goes between Ellesmere Island and Greenland. And you can see the ice actually be advected or flushed out of the Arctic through that strait. So this is a composite animation of basically daily images covering multiple months. And again, we couldn't possibly study how sea ice moves, why it moves. And of course, tracking sea ice is important if you're in a ship, if you're trying to move across the Arctic. So we couldn't possibly understand the dynamics of sea ice in the Arctic if it wasn't for satellite data. So again, a really important perspective on our planet. I'll get off of that slide. Okay, another reason why we need satellite data. This is an image of a precipitation gauge. So this is something that we use to measure snowfall in the winter. It's really useful to make measurements on the surface of the Earth as well. The space is great, but we have to make measurements on the ground as well. What you can see happens is the snow actually sticks to the top of this precipitation gauge, starts to block off the top, and the measurements themselves become pretty sketchy as we move through the winter season. So the surface networks we have are important, but they have limitations in how well they can measure things. So combining our surface networks with the instruments we have in space is super helpful. So some people are surprised by how many satellite missions we actually have. So this is a really cool graphic from the European Space Agency. So the European Space Agency operates a massive fleet of different satellite sensors that do different things. They have a whole family of science missions that are motivated to measure particularly new elements of the Earth system that we haven't measured before. So kind of pushing the envelope of the types of measurements we can make from space. The Copernicus family of satellites, these are more operational. So they have a sustained life cycle where one instrument starts to get old, they launch a new one to take its place. So these are really important series of satellites that monitor our planet. And then meteorology, this is a huge driver. All of our weather forecast models are driven by information that we get from space. So these are only the European sensors. I like this image because it shows the whole suite of instruments. NASA, of course, operates a lot of instruments as well. The Japanese Space Agency, JAXA, the Canadian Space Agency, as Aris talked about already, we have instruments in space as well. So there's really a busy ecosystem out there of instruments operated by different agencies. But what's really cool is that most of the data from all these missions is freely shared between countries. So different governments, scientists, agencies, we can all use these data and share the data freely and openly. We don't always use satellites. I just wanted to put, if you're interested in aircraft, we also put instruments on aircraft. This allows us to do very targeted measurements that are a bit harder to do from space. This is an aircraft, part of a program called the Airborne Snow Observatory, which is operated in the US. And they can produce these really cool, detailed snow depth maps that look like this. This is for one small watershed in the western US in the mountains. And we could not resolve this kind of detail with instruments operating in space. But when we put instruments on an aircraft, we can get really controlled, high resolution data. So that's pretty cool. What we really need to do, though, is research to take, as I mentioned, these raw satellite measurements and convert them into the variables that we care about. So what this slide is showing is, again, it's from the European Space Agency. It's all the suite of products that they take all those satellites I showed previously, and they convert them into things like river discharge, soil moisture, constituents in the atmosphere like ozone, the biosphere, the cryosphere, that's ice and snow. So it's really a rich research program to take the spaceborne measurements and convert them into the variables that scientists want to use. And so this kind of flows a little bit like this, where you have a raw image from space. So this is what we call level 1 product from a satellite. You can see Greenland here on the left, Canada on the left. This is the whole northern hemisphere image. Then we convert that into products. So it's basically a snow depth product I'm showing in the middle. And then we have these products now for multiple decades. So we can analyze those and produce a map like this on the right, which is a trend in the snow depth across Canada. So it's this flow, this process of you make a measurement from space, you do research to convert it into a product, and then you do analysis of that product to produce information that people want and need. So the real key aspect of understanding the satellite measurement and getting it to a product, the part that I like about my job is getting into the field, making measurements on the ground to make sure we're interpreting the satellite data properly. And when we think about snow, what are the kind of questions we're trying to answer? Well, like when you dig in a snow pit, when you play in the snow, you realize snow crystals are not the same shape. There's different types of them. They evolve during the season as snow sits on the ground because wind blows snow around, temperatures change, maybe it rains, and then the snowpack freezes again. So lots of dynamic things happening in the snowpack that we have to measure and understand so that we can interpret the satellite data in a correct way. And just to zoom in on snow a little bit, I'm a snow scientist, so I have to show you this in a little bit more detail. This is what snow looks like from the top left when it first falls. These are classic kind of stellar dendrites, they're called, the classic snowflakes that you make from paper at this time of year. but then the wind starts to blow the snow around. Maybe it gets a bit warmer, so they start to kind of round off all their edges, and then they go down to this bottom right image here where you get these rounded grains. And then what's really cool is if snow sits on the ground for long enough, like multiple months, and it stays nice and cold, you get these large faceted cups that form. And it's a bit maybe hard to tell from this photo, but these grains can be the size of my thumbnail. They get really big. So it's really cool to try to look at, how the snow evolves during the season. And what the satellite sees looks quite different if the snow looks like this in the top left, or if the snow looks like this on the bottom left. So we have to understand the physical structure of the snowpack so we can interpret the satellite data properly. So just a few more photos. This is now the sort of travel log part of my presentation. We have a field campaign going on in Western Canada right now. Some of my colleagues just got back. They're working in the mountains in Western Canada, just showing some of the measurements in a snow pit here, making very precise measurements of the snow grains. We also have a radar system on this rail. So this is very similar to instruments that we fly both on aircraft and in space. But by deploying it really close to the snow, we can kind of zoom in and really understand exactly how the microstructure of the snow is impacting our radar measurement. We also put, as I mentioned, instruments on aircraft. So this is a photo from a few years ago in the Arctic where we were flying a LiDAR instrument on that aircraft there. And finally, because I said this is the travelogue part of my presentation, the thing I really like about my job is getting to see some cool things. I'm very fortunate to get to travel in the Arctic. Just a couple quick slides. Got to see some muskox. That was pretty neat. We one time camped with some Inuit elders who came and built an igloo. They thought we were pretty strange to go out measuring the snow the way we were every day. But we had a great time spending time on the land with them. Got to see some northern lights. And most recently, I managed to go to the Greenland ice sheet for the first time. So I went to Greenland in June, got to measure the snow on the ice sheet. And we went to a place where this big sort of golf ball is, where they just finished drilling 2 kilometers through the entire ice sheet to get to the base of the ice sheet. So that was pretty cool to see that drill site. So all this to say that remote sensing has led me to some pretty cool places. I'm very lucky to be able to go to the places I've been to measure snow, and all of this is to support how we use spaceborne data. So just a couple thoughts to end on before we discuss your questions. Remote sensing really is a fascinating field, and I think Ara showed this through the evolution of missions, how we come up with new ideas, how we build things and launch things, and we really rely on data from space to provide critical information to us on the structure and constituency of our atmosphere, how our land surface is changing, how snow and ice are changing, how our oceans are changing. And if you think you have an interest in this, there's many, many different fields. So I'm kind of an earth scientist. So I study, how we use the data to answer some of these earth science questions. But if you're interested in sensor development, satellite technology, orbital dynamics, algorithm development, field work, there's so many different subfields that it's really a rich area that you could think about getting into. And again, just to bring us back to the Space Brain Hack, I'm sure you all have some great ideas now. So please take a look at that website and get involved. And I will stop there and we'll take your questions. Thanks a lot for listening.
Thank you so much, Chris, for sharing all this beautiful information with us, especially how important it is to study snow and sea ice and the complementarity between the work done in the field and the satellite measurement and imagery to understand better our climate. So thanks again. So this is a general question, so feel free, Chris or Ara, if you would like to answer. So the question says, what aspects and or stages of the mission would you like the students to focus on?
Actually, it's up to the students. So we know that there's so many different sections that it's too complicated to think of an entire mission. So when you go onto the website of the Space Brain Hack, there's a guide that will give you kind of questions that you can ask to get the reflections going for each of the different stages. And then based on those reflections, there might be one stage that kind of jumps out at you more. If there's one that jumps out at you more, that's the one you want to focus on. And Ara, if you want to add something from your experience as well.
Yeah, absolutely. I think, again, every engineer and scientist has a bias. For me, the bias really comes down to all the things that we don't look at. So, not just the small little satellite itself. I mean, relatively speaking, it's smaller than a bus. So, how much materials could there be? But all of the other thing that goes into it, the testing, the support equipment, the equipment for engineers, um, transportation. But the scientist in me and the engineer in me would be fascinated if you find alternative materials for satellite stuff as well, like hydrogen and things like that. That would be cool too.
Thanks, Isabel and Ara. I have another general question that says, how much does the average shuttle cost to build and launch?
Okay. So the cost goes anywhere from to build, including launch, for a tiny little CubeSat, it could be something as small as 15 to 20 million, all the way up to the James Webb Space Telescope, which is like 4 billion plus. So it really depends on the satellite, the mission. Now we're trying to find ways of doing super precise measurements that you would normally do with a giant telescope like Hubble by using tiny little CubeSats working together, flying in formation and making like a virtual mirror together, for example. But it's an upcoming generation of satellites to try to do the big task with smaller things. But if you launch something like Hubble or James Webb again, it'll be costing billions. And meanwhile, universities and high schools, all the high schools in the US and EU and also in Toronto, I think, have launched CubeSats for budgets in, the couple of million or less. So it's amazing.
Thank you so much, Ara. And since we were talking about satellites, there's a question also that is coming from one of our participants asking about the type of camera used in a satellite. So is it a specific type of cameras that are allowed to be used on satellites in order to get the imagery that we were talking about?
So there, by camera, such a vast field. So by camera, you literally, we try to generalize it and say it's a device that collects light and stores the information that was in the light onto some kind of medium, like a chip. Back in the 50s, they used film cameras and they would drop the film cameras and then somebody had to go and retrieve them. But now there's many, many different types of cameras. So you could have, for example, a device like a solar occultation spectrometer that only registers the amount of light in a certain frequency that goes up and down. Or you could have a full scale, 3D video imaging system. Or you can have infrared cameras. Or you can have something like the radar sat, which is a synthetic aperture radar. So it receives our radio frequencies actually and converts the radio frequencies into like imagery information for the ground. So by camera, we mean anything that collects light information and puts it on a screen or some kind of medium that we can look at it like an image. So we study all sorts. We study gamma rays, we study, all the way to microwaves. So any type of camera you want to use, there's a mission for it.
Thank you so much. So fascinating to learn about all this technology. And there is a question that illustrates already the creativity of some of our students. That is more about the debris that are left in space. And the question says that, is there a way, for example, to use magnets or any tools, any existing tools, for example, it's the question mentions the Canada arm, to attract and collect these debris from the space?
So there are multiple things. The first off is that we would never, ever, ever use the ISS to attract any debris because there's a chance that something could go wrong when we're attracting debris and attracting these things flying around, and when we endanger the lives of the astronauts on board. So the ISS is no, 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 not allowed to endanger the lives of the astronauts on board. So that's a safety problem. The second thing is that in space, there is no friction, there is no air, nothing to nothing to absorb the momentum of something that's flying towards you. So for example, if you had a screw that was coming the opposite direction from you in space, you're going 7 kilometers a second one way, the screw is going 7 kilometers a second the other way. You change its orbit a little bit by having a magnet. So the next time it comes around, it comes closer and closer to you. Now it's hitting with the momentum of 14 kilometers a second. That's probably not going to stay on the face of your plate. It's going to deform your magnet. It's going to punch through your system if it's small enough debris. So it's to attract debris to you is not always the best approach to do it. In theory, if you had a giant magnet rolling around in space, the next question you have to ask is how many materials that you use for satellites are magnetic? We don't tend to use magnetic materials. First of all, because they're heavy. Second of all, anything that has a magnet in it interacts with the magnetic atmosphere, Earth's magnetosphere, and induced magnetic currents. We use magnets actually for reaction wheels. We use them for very, very sensitive instruments. So if you put a giant piece of iron or something else that's ferromagnetic out there, it can interfere with the operation of the satellite. So not a lot of satellite things are magnetic. So it's a for some types of debris, some stainless steel, some things, you could, in theory, put a giant magnet out there, but it may not be worth very much and it may get destroyed super fast. So it's a viable thought, but I don't immediately see how we could do it or how useful it would be, let's say.
Now I have some questions for Chris. And the first one saying, when looking at the map of Canada, why is it warmer on the west versus the east?
That's a great question. So when we think about how temperatures have changed across Canada, there's a number of different factors at play. So one is that we know the climate change signal. So temperatures, are globally, almost 1.5 degrees warmer than they used to be. So there's this imprint of global warming. But then there's also regional differences that are driven by very well understood what we call climate feedbacks. And actually, snow and ice drive one of the critical climate feedbacks in the Earth system. And as the Earth gets warmer, we have this global warming signal. Snow melts earlier in the spring. Snow is really bright, right? It reflects a lot of light back into space. So that snow is gone. You have a darker land surface, actually absorbs energy from the sun. That leads to more warming. That's a positive feedback. Gets warmer, less snow, warmer, less snow. Like a snowball rolling down a hill is a bad example to use. But anyways, so because of these feedbacks, northern countries like Canada are warming faster than southern countries. So that's another part of the system. And then also there's just natural differences regionally because weather and climate is inherently kind of noisy, right? The weather is different every day. Things evolve in the atmosphere in kind of a chaotic manner. So when you have this combination of global warming, climate feedbacks, and then natural regional differences, it recreates these regional patterns that we see. So right now, since 1950, northwestern Canada has warmed more than eastern Canada. But as we go more decades into the future, that pattern may not stay the same. We could see some differences. It will definitely be warmer, but how much and where exactly is still a bit of an open question.
Thank you so much. And when it comes to snow calculation, is it possible to calculate the amount of snow that is falling only from space or only with satellite imagery, or does it take also field work?
That's a great question. And there's an instrument in space called GPM, the Global Precipitation Mission, and it's actually a constellation of satellites. And they have sensors on board that are able to measure rainfall and snowfall. But they work better over the oceans than over land, and they measure in a very narrow swath, so they don't cover a large area. So it's hard to comprehensively monitor precipitation, snowfall, rainfall everywhere all the time just from space. So what this question actually is leading to is like super interesting in the sense that like when we really want to analyze satellite data nowadays, we typically have the satellite, we have some observations on the ground, and then we have some sort of modeling system that brings all the information together. So satellite remote sensing doesn't really exist in a vacuum where we just take the satellite measurement and we analyze it all on its own. Nowadays, the state of the art is sort of combining the satellite measurement with some ground observations and some sort of physical model. So it's getting more complex, and certainly AI tools, other things like that are helping us out a lot. But we're moving into this area where we want to analyze all the data together. That was a really excellent question.
Thank you so much, Chris. And just for time considerations, we will be taking only one last general question. And Chris or Ara or Isabel, feel free to answer. The question says, if satellites can have an impact on climate change.
Well, maybe I'll go first, and I'll just say absolutely. They already have had and will continue to have an impact on climate change science because really without information from space, we would struggle a lot to be able to quantify the rates of change, where things are changing, why things are changing. It's the coverage, the information, the comprehensive level of data we get from all these different satellite systems is absolutely critical to monitoring our Earth system. And I think there's an increasing realization of how important data from space is. It's driving agencies to work together to share data openly and freely. Certainly, the number of missions are larger now than they have been in the past. The breadth of ideas is increasing. So I think there's a real awareness of the really important role that remote sensing has in helping us understand climate change.
Yeah, from my side, I would just quickly add that we're finding that the edges of the world, so the Arctic, the oceans, the upper troposphere, things like this are very, very, very important to monitoring climate change, and sometimes these are the most vulnerable areas. And normally, it is not possible without satellite data to get this information. It's just not possible. Maybe you send one mission there and you get a few samples. You go a couple of times, you put one monitoring system there, but having global everyday coverage in order to compare, how it's changing is absolutely impossible without satellites, in my opinion.
I think I'm going to play the devil's advocate. And I'm going to come back to the fact that we did talk about the importance of satellites for climate change science, but building the satellites, launching the satellites can produce greenhouse gases, which can have a negative impact on climate change. And that's the challenge, is how do we keep this super important tool that we absolutely need to make sure we protect the planet? How do we keep it, but reduce any greenhouse gases or pollution that can come from using it? So that's the challenge. That's what we've got to go out and figure out how to do.
And this is why we invite you and encourage you to take part to the Space Brain Hack Challenge. So thanks again, Isabel, Chris, and Ara for your time and sharing with us all these valuable information and also your experience. We have to end our webinar right now. So thank you also to our participants, and we hope to see many ideas shared through the Space Brain Hack. So thanks again, take care of yourself, and see you next time.